Class 44, we are practicing calculating tangential velocity, centripetal acceleration, centripetal force, and some applications of it. So here's a question similar to ones we've seen before. First thing you have to do is you have to find the tangential velocity. So to find the tangential velocity, simply distance over time, but remember the distance is the circumference of the circle because it's time we're given is the time it takes the rubber stopper to go around the circle once. So the distance would be the circumference here, so we get 6.13 meters per second. Here's a little picture of what's going on. Tangential velocity points out tangent to the circle. Centripetal acceleration and centripetal force always point toward the middle of the circle. What is the centripetal acceleration of the stopper? V squared over R. 6.13 squared divided by 1.2. You get 31.3 meters per second squared. Now to get the next one, the centripetal force, just be careful. You have to make sure the mass is in kilograms. So 15 grams becomes 0.015 kilograms. Kilo means 1,000, so you got to move that decimal place 3 places. So two ways you could do this. You could do Fc equals MAC, or Fc equals mv squared over r. Since you already have AC, this way is a little bit quicker. So you just take AC, multiply by the mass, and you get 0.47 newtons. Or if you want to start from scratch, m is 0.015 kilograms times v squared divided by r. You still get 0.47 newtons. So the centripetal force here is equal to 0.47 newtons. But remember, the centripetal force always has an agent. Like what causes that 0.47 newtons? In this case, it's the tension in the string. So the tension in the string is the agent of the centripetal force. Therefore, the centripetal force is equal to the tension in the string. Therefore, the tension is equal to 0.47 newtons. It looks like a roundabout way, but just keep that in mind. The centripetal force always has an agent. Whatever the agent has, or whatever the agent is, in this case tension, is equal to the centripetal force. So if you kept the velocity constant but changed the radius, how would the tension change? So how would the centripetal force change? Well, centripetal force is mv squared over r. That's all the variables in there. So we notice that there's an inverse relationship. We'll start talking about this more and more later in the unit, but this is an inverse relationship between centripetal force and r. So if r gets bigger, centripetal force gets smaller. If r gets smaller, centripetal force gets bigger. Just put in some numbers, try it out. Like instead of making r 1.2, make it like 0.2, way smaller. See what happens to the centripetal force. Make it 2.2, make it bigger, and see what happens to the centripetal force. So again, centripetal force in this case is the tension, so whatever change happens to the centripetal force is happening to the tension. This is another way we like to write this, that centripetal force is proportional to 1 over r. Here's some example problems here with a toy plane going around a circular path, 10 complete circles in 30 seconds. So each one circle, takes 3 seconds to complete. The radius is 4 meters, so v equals 2 pi r over t, because the distance is the circumference of the circle. So 2 pi times 4 meters divided by 3 seconds, because it takes 3 seconds to go around the circle once. So you get 8.4 meters per second. There is another way to do this question. You could, instead of doing the time to go around the circle once, you could make the time 30 seconds, multiply the circumference by 10, because it goes around the circle 10 circles in 30 seconds. So you can multiply the circumference by 10 and put 30 seconds in the denominator. You'll get the same answer. Try it out. It's a good practice. Now the next question here, we have 1.0 times 10 to the 3 kilograms. There's a car, and it travels at a constant speed of 20 meters per second around a horizontal circular track. The diameter of the track is 1.0 times 10 to the second meters. The magnitude of the car's centripetal acceleration is, so that's just v squared over r. Now, be very careful. We're given the velocity or the speed, 20 meters per second, but we're given the diameter of the track of 100 meters. Make sure you divide that by 2 and put it in for the radius. That'd be 50. And we get 8 meters per second squared. The next part is the Earth going around the sun. So we just kind of drew a picture of what's going on, centripetal force and centripetal acceleration pointing towards the center of the circle, or towards the sun in this case, and velocity pointing tangent to the circle. What is the agent of the centripetal force here? It's the force of gravity. So if we calculate the centripetal force, we calculated the force of gravity. So let's do that. Let's calculate the centripetal force. So there's a lot of work here, but let's look at some of the stuff from our reference table. So I'm not going to write this all from scratch because the numbers are big and I don't want to mess them up. So first things first, write our givens. We get the mass of the Earth, that is from the reference table, 5.98 times 10 to the 24 kilograms. The radius of Earth's orbit, that's the distance from the Earth to the Sun, is 1.5 times 10 to the 11 meters. And the period of Earth's orbit to go around once is 1 year. Got to convert that to seconds though. So second thing I did was I converted the time to seconds. 1 year times 365 days in a year times 24 hours in one day times 3,600 seconds in an hour gives me 31,536,000 seconds. So that's our time to go around once. Now, this is all the math we've done before. These numbers are just much bigger. So to get the speed of the Earth in its orbit, V equals d over t. D is a circular path because we're going around the sun in that given amount of time. So we have 2 pi times 1.5 times 10 to the 11 meters. That's the distance to go around the sun. Divided by the time it takes to go around the sun, we get 29,900 meters per second. Roughly, that's a little estimated. Then we just took that number, along with our mass and orbital radius. We threw it all into our calculators, carefully making sure to put the denominator in parentheses. We should get 3.56 times 10 to the 22nd newtons. That is the centripetal force acting upon the Earth. Therefore, that is the force of gravity acting on the Earth, because the force of gravity is the centripetal force. It is the agent of the centripetal force here. So if the Earth is feeling a force of 3.56 times 10 to the 22nd newtons, the sun is feeling the same force. That's what Newton's third law tells us. If the sun pulls on the Earth with this many newtons, the Earth pulls on the sun with just as many newtons. This is a nice tie-in to the next unit that's coming up, where we start talking a little bit about gravity.